So welcome to Stop and Think, Learning Counterintuitive Concepts in Science and Maths. Denis and I are just working on behalf of a team of probably over a dozen people, plus the research assistants who visited all of the schools in the trial. So it's just a small tip of the iceberg that you've got. One of the things that we'd like to get out of this, or we hope you can get out of this, is a couple of questions which we'd like you to think about as we go through the presentation, because it wasn't just the research we were interested in, it was also about how we could interlink what goes on in practice, as well as the research findings and the way we conducted the research. So one of the key questions, looking back and reflecting on this, is what might this mean in the classroom? What are the findings telling us? For example, does it tell us something about the influence of existing knowledge and misconceptions? Does it tell us something about the time to think and reflect, the guidance in transfer of the reasoning processes? And what does it tell us about the maths, the differences between maths and sciences and the way children respond to it? And the second big question is, how can we use research better to inform and influence classroom practice? You know, what areas do we need further research? What type of approach should be used? And how can we involve teachers and researchers more effectively working together rather than it seem to be one direction only? So without more ado, we'll move on to the actual project itself. Just give a little background to UnLocke, then go through the Stop and Think activity in the project design and the findings, and then we'll come back to the Q&A and what you think and your contributions towards the end. We will aim to finish this whole thing by 6:15 at the very latest, but obviously that depends on you and whether you keep asking questions or not. So why UnLocke? Well, UnLocke basically started out as part of a series of projects which were funded through the Education Endowment Foundation and the Wellcome Trust. And it was based on the idea that people were doing work in educational neuroscience and related areas, whether there were things that could be learned to influence classroom practice. There were 6 projects funded, of which the UnLocke project, Learning Counterintuitive Concept, was one. They've all now published, and the reports are on the EEF website. The UnLocke started really from what do we know about learning counterintuitive concepts. And one of the things the research tells us is that the learning often requires inhibition of those prior beliefs and direct perceptual solutions. And we'll give you some examples of those. And it also means that inhibitory control as a process within the brain seems to be a key factor in cognitive development. And what we wanted to test out was whether this had any influence or impact in practice. So, first question coming up. Is this circle 1 bigger, smaller, or the same size as circle 2? So if the quiz question can come up, you can put your answers in now. So if you put your answer in where you think it is, what you think the answer is, and then submit it now, we can come up with what everybody's saying. We get the answers up. Peter? Oh, there we go. So almost equals, smaller or the same size. Obviously, I guess most of you have seen the question before. The answer is they are the same size. But when you look at them, they appear to be different. And very often, particularly in young people or people who haven't seen it before, they will go for 2 being bigger. And it's all to do with the way we perceive the question in relation to the circles around it. If we go on to the next question, if I can get my screen to work. There we go. In general, are elephant cells bigger, smaller, or the same size as mouse cells? And if you could submit your answers, please. and get the results up. Same size. Again, we have that information available to us. We've learned it. We've sort of embedded it. But again, if you think about what young children do, they tend to respond that they're bigger, which obviously a couple of people have indicated that. And it's about that perception again, and understanding of what's going on behind the skin, if you like, in this situation. And the final question, oops. A bat and ball cost £1.10. The bat costs £1 more than the ball. How much does the ball cost? Does it cost 5, 10 or 15p? So if you can put your answers in quickly, please, and then submit it, and we'll get the answer coming back. And the answers, 50% 5p, 40% 10p, and 10% 15p. Again, the question asks how much the bat is £1 more than the ball. We tend to get hooked on the £1 and 10 pence, and therefore very often the knee-jerk reaction becomes the 10p version, not the 5p, which is the correct answer. And in a way, that's going on all the time. We're learning, particularly things that are counterintuitive. How do we actually address that? And it seems that in the brain, from the research there is, that reasoning that is consistent with prior knowledge tends to use one neural system, and where it's different, where there's a conflict, other systems are used. And particularly with the science reasoning, there are two particular areas that seem to contribute to this. They're not the only areas, but they are the particular ones. The ACC, the anterior cingulate cortex, tends to identify when a conflict. So it actually acts as a bit like a gatekeeper. If there's conflict, it goes one way. If there's no conflict, it goes another way. And then the dorsolateral prefrontal cortex, which is at the front of the brain in the frontal cortex, actually resolves the conflict. And Denis calls these the Batman and Robin of neuroscience. The AC is Robin, who says, Batman, we've got a problem. And of course, Batman goes and sorts the problem out. And again, people have done some work on this. So I'm not going to ask you to answer this particular question, except just to think about what you would say is the answer. This was some work that was done by a group in Canada using experts and non-experts who were physics graduates and non-physics graduates, basically. So you would expect the physics graduates to know the answer fairly straightforward, and the others may be less sure. So set question 1, that is showing 2 lit bulbs, but it's clearly not correct because the bulb on the right, as you look at the screen, is not connected to the circuit. So that one is not correct, and it was used as a control. The second one is a non-scientific circuit. Both bulbs lit up, but it appears that the circuit's all intact, when in fact, we've only got the bulb on the right is only connected by a single wire. Therefore, it's not actually part of the circuit. So that circuit is also incorrect. And it is in fact the C, which is a scientific circuit, where the bulb on the right is not lit up because it's only connected by that one wire. So by giving tasks similar to this, the group actually compared experts against non-experts. And the interesting thing was that the experts activated brain areas involved in inhibition much more than the novices, which is sort of in itself counterintuitive. And the explanation that they proposed was that the experts seem to hold the misconception within the neural networks, and that what they are able to do more effectively than novices, because they recognize this is counterintuitive, they can inhibit that thought and then come forward with the correct scientific answer. And it was based on this supposition that the UnLocke project went ahead. If this is what's happening with experts and non-experts who are fairly well advanced in their learning, what does it happen to younger children? Obviously, we've got a range of behavior and brain imaging studies that have contributed to this sort of work, but almost the work is conducted with adolescents and young adults. So whether the same thing happens with young children is something that we didn't really know. And that is compounded by the fact it's difficult working with young children. They get distracted, they don't always focus. So again, we've got particular challenges. And when you're going into actual scanning situations, the lowest age range there is about 6 that's being used, because most children can't stay, never mind the whole frightening noise that you get with a scan. So basically, UnLocke, using the research and developing the concept, if you like, from the research, that we know in science and maths, there are quite a number of counterintuitive issues, whether they're from intellectual points of view or perceptual points of view, they lead to misconceptions. Can we actually improve the situation, the way that children deal with that? We also know that the misconceptions are actually quite resilient and long held, if in fact they ever go away. We don't know about that, but they do resist change. Therefore, the argument is that improved ability to control this initial answer, this intuitive response, that would help learning. And there is some evidence that suggests that children with low socioeconomic status have inhibitory control impaired more than others who are perhaps a little bit more privileged or less disadvantaged. And the other issue is that it seems that from certain aspects, if you teach executive control for processes as in isolation, the transfer to new areas doesn't work very well. Therefore, this particular project, we looked at the context of using inhibition as part of the maths and the science activities that the children would be normally doing. So we weren't teaching inhibition in isolation from the topics that they were dealing with. So I'll hand over to Denis, who will outline the project and the findings that we got. Over to you, Denis.
Great. Well, thank you very much, Derek, and thank you everyone for coming to this session. I just want to reiterate what Derek was saying. I mean, the goal of this session is in part to kind of disseminate the findings for those that are interested and for the schools that were involved in the study in the first place, but also really to get feedback from you, you know, as to how we could improve what you think of the ideas. You know, is what we're doing completely daft? We should not pursue this, or you know, are there really important ideas that could be pursued and applied in the classroom? So, as Derek said, my role here is going to be to talk about the implementation of the intervention, how we went from these basic theoretical findings that Derek outlined to something that we could do in the classroom to improve performance on math and science, and then the evaluation results. How did it work, and so forth. Oops, sorry, Derek, I think next slide, you're controlling the slides. Yep. So just to remind everyone, the key idea of the project is really to enable children to use their existing inhibitory control skills in the context of math and science. That is, not to jump to immediate conclusions. So do you remember when we did the few test questions there about the size of the elephant cells and the math problem with the cost of the ping pong ball? Derek was quite keen to get you to act quickly, to respond as quickly as you could. That's because it would prevent you from engaging your more kind of rational, analytic reasoning system, which is a little bit slower to engage. And what we want to do is to get the kids to stop, not to blurt the first thing that pops into their mind. You know, when I say things like, if you ask them questions like, what do cows drink? Well, it's not milk. It's water like everything else, right? But for almost everyone, milk pops into their mind first. So we need to stop that to allow them to activate the kind of reasoning rational system and bring out the kind of more deeply entrenched knowledge. Stop and think before responding. So here it's going to be a very rapid overview of the program, what we think are the key elements to give you a flavor for it. And on the slides here, we have our website for the UnLocke program, where you can find out lots more detail, the scientific background, the videos presenting the results as well, and the final evaluator reports as well. So Derek, next slide, please. Okay. So quickly, as Derek said, this intervention was basically based on some findings with adults that specialists in science were basically better than novices. Experts were better than novices at inhibiting these kind of very familiar lay concepts, which were incorrect. And so the idea behind it is, well, maybe if we improve inhibition skills in children, they will also be able to kind of apply their more experts formally acquired knowledge. So in order to develop this, deliver this intervention, we embedded it within a computer game, right? So it's important to understand that the computer platform is not part of the theory or at the heart of the intervention itself. It's just the kind of support that we used for ease of delivering the same kind of experience to as many children as possible. But I can imagine that one could develop a less technology intensive version of this with kind of cards or games and so forth that would still kind of train the inhibitory control. So Derek, please, next slide. So the game was embedded in the context, or was created in the context of a game show. The children were presented, or the class was presented with a panel of experts, Candice, Oli, and Kate, and Andy, I keep forgetting Andy's name, actually. Andy, who's the character, was the game show host who would ask the questions and lead everything. So here's the game show. Derek, if you'd like to show the next slide. The children were then presented with a problem like this. What number is shown here, which was a problem that drew on well-established misconceptions in children of the particular ages that we targeted, and I'll tell you about that. So we went through books of concepts that children have difficulties, lots of misconceptions too. Here, one easy misconception is to think, well, there are actually only 7 objects here, so the answer should be 7, when in fact each of the rows represents 10 objects, and so on. So the children would have a few minutes to think of a possible answer, and they could type their answer in the box. So Derek, if you want to move forward. Sorry, I forgot to say, of course, we're training them to stop and think. So they can't type the answer in the box immediately. In fact, every question is followed by a 5-second interval where there's this big red hand saying stop and think. And at that point, the keyboard is frozen, so they can't interact with it. They're forced to stop and think about it, which would give them hopefully a bit of time to allow the kind of real answer, the correct answers, to come forward. So Derek, if you'd like to push the next slide. So once they've provided an answer, if it's correct, they're presented with some options by the different candidates. For example, Candice would say, oh, I've counted 7 pieces. Oli would say, oh, there are 4 long bars and 3 squares. And Kate would have 4 bars each, and so forth. And Andy would ask them, to choose which child had the right answer and why. And they could go through several iterations of this. If they had the right answer, they would move on to the next phase, which I'll describe in a minute. If they had the wrong answer, there would be several cycles with more scaffolding of what the answer could be, an explanation, and so forth. So Derek, if you move on to the next stage, once they got the answer correct, they then moved on to a series of what we call structured practice trials. This was basically presented to them as the bonus round. Yay, you've got it right, so you get to play the bonus rounds. It's amazing, if you call something a bonus round, it motivates children a lot more. And then they had a series of problems based around the same concept. Each of these sessions, which they played, involved both math and science activities. So Derek, if you want to advance, we had stop and think, of course, each time. And each of these problems, they have the 5 seconds stop and think. Remember, stop and think, so they can't give their response immediately. So Derek, next slide. And so this is an example of some of the science. This is year 3 curriculum, I believe. Some of the science they had. So, which of these animals is a fish? And they would click on the fish ones. But of course, before they could click, they would have the stop and think. Here's another example of the same sort of problem, just presented in a different way. So it was a sorting type of example, which of these animals are fish? So they had to put all the fish in the left-hand bucket and all the non-fish in the right-hand bucket. Again, they can't respond before having waited 5 seconds. So Derek, next slide, please. Okay, so that's really what's happening during the game, during the intervention. What were we targeting? What was the project about? So we targeted year 3 and year 5 children. The content of the problems was based around the national curriculum for year 3 and 5, the problems they would have. Over 6,600 children took part across 89 schools in England. And each of the sessions was 12 to 15 minutes. So 12 minutes of interacting with the game, plus a few minutes of faffing while everyone got themselves sorted, 3 times a week for 10 weeks. And we asked the teachers to deliver it within the first 10 or 12 minutes of any math or science lesson as well. Now that was the intervention. How do we evaluate the intervention? Well, you can evaluate an intervention by comparing it against the performance of other children, but what other children? So one option is children who basically have business as usual. So you can see, well, those that were in the intervention group, you know, their math and science performance scores at the end increased by more than those who were in business as usual teaching. But that could be for a number of different reasons. It could be, for example, for a placebo effect, or what in psychology is called Hawthorne effect. The idea that if you know you're in an intervention and you're being studied, your performance will go up just because you know that. Possibly you pay attention a little bit more, possibly the teacher delivers with a little more energy and so forth. So what we do is compare the performance of the intervention children playing the stop and think game against what we call an active control. So these are children that are also playing a different game using the same characters, similar graphics for the same amount of time, but it's not targeting the inhibitory control skills and not delivering math and science curriculum. Instead, it's delivering kind of social skills training. So this was our C+, which delivered elements of the PSHE curriculum for year 3 and year 5. In addition to this, these 6,000 children, we also tested some 370 children on a more in-depth kind of cognitive profile, cognitive battery, and 52 of them were also scanned pre and post intervention. And this was really to try to get at to make sure that the mechanism, if our intervention did work, we would understand exactly why it worked. So as Derek said, lots of the evidence for this was based on studies with adults and teenagers. And we really wanted to make sure that the same thing was still happening in children. So we had to do a more in-depth study. That's a kind of a side project, but just to let you know that we kind of collected this and we're still working on analyzing these data. So Derek, next slide, please. Okay, so this is just to kind of make sure everyone understands the structure of the study. So we have all the classrooms. These classrooms were split between control groups and intervention groups. Half the classes got the stop and think intervention. The other half were the controls. We're going to compare the performance of the stop and think to the controls. But within the controls, we have 2 different types of controls. One is the business as usual. The other one is the C+ active control. So we'll be able later to compare the intervention children against maybe the C+ active control and make sure that any gains we get aren't because of a kind of placebo. The allocation to the classes were done by the NFER, so the National Federation for Educational Research, and they were appointed by the Education Endowment Foundation as the independent evaluators. So they had nothing to do with the design or development of the thing. They went into the classrooms afterwards to kind of test children's performance so that that final evaluation wouldn't be biased by any kind of unconscious bias we as the developers might have had. Just to give an example, the other thing we did in terms of allocations is that in each school, both the year 3 and the year 5 took part. And one of the 2 years in that school would be the active intervention. For example, year 3 might be in the intervention, and then the other complementary year, the year 5 in the same school, would be allocated to one of the 2 controls. So maybe to business as usual, maybe to C+. And one of the advantages of doing this is that every school always had one of the active conditions. And that's really important because lots of schools are attracted to a program because they think it's really, cool, it has potential and so forth. And then if you then allocate them to the control business as usual and tell them, actually, you're in the condition that doesn't get the intervention, they're not happy. So in this way, every school always had part of the promising intervention. So Derek, next lesson. So what else did the NFER do? As we said, they did the allocation of the classes, so we had nothing to do with that. They also did the standardized testing. The performance of the children in math and science was evaluated using standardized math and science assessments produced by GL Assessments. They did that in math and science. And half the children, so remember, each of these sessions, 12-minute sessions, involved 6 minutes of math, 6 minutes of science. So they did both math and science training, or rather inhibitory control training in the context of both math and science. Or everyone did that. But we only evaluated the children either on math or on science. This is so that they didn't, have too much of a burden, have to sit through a 1-hour test and then another 1-hour test. So half the children were randomly allocated to be evaluated in math, and half were randomly allocated to be evaluated in science within a particular classroom. Okay, so it wasn't one class does math, one class does science. Everyone did both, just half of them did math, half of them did science test. And then the NFER also did face-to-face and telephone interviews with the staff, and we have some qualitative feedback that I'll tell you about. And then they did the stats, the evaluation report, and published the evaluation reports. We did some post-testing as well. So we went in, and after the NFER had finished, went in and tested whether this intervention had any effect on children's inhibitory control in general. And also we did this kind of subgroup detailed analysis that I mentioned early on, but again, I won't be talking about that today. So Derek, do you want to step forward? Right, so the project was cut up into 3 times. It took quite a while to do. The first phase lasted about 18 months, and this was what we call a development phase. And what we were doing here was trying to kind of identify what the best mode of delivery of the intervention would be. So on the one hand, we thought, well, it might be best to have individualized delivery. So every child is in front of their own computer, playing the game at their own rate. And then this would allow us, different children to go through different problems depending on their performance level, or whether it should be a whole class delivery process in which maybe the teacher plays the game on using a projection screen or an interactive whiteboard board with the whole class sitting on the carpet or whatever the setup is and engaging at the same time. A pilot study involving 9 schools showed that actually the whole class mode of intervention was the most effective one. And here, most of the issues were technology issues. That if you're trying to do an individualized delivery, you need to make sure that all the classes all have enough working computers of sufficient power to support the game. And that wasn't always the case in many of the schools we went to. So in terms of efficiency or efficiency of delivery, the whole class was the better option. Then from July 2017 to April 2018, we ran the intervention, the main trial, and had it evaluated. And now we're in phase 3, where we're basically, we've done the analysis, we're feeding back and getting, disseminating the results, getting feedback from you and others on your ideas on this. And we've also kind of developed a new version 2 of the game in light of some of the comments that we've received before. And as a heads up, this version 2 will actually be part of a larger efficiency trial that is being run by the Education Endowment Foundation, not this coming year, but the next academic year. So Derek, do you want to tell us? Okay, so that was the intervention. What happened? Did it work? What were the conclusions and the lessons that we could draw from that? So let's start by saying that some of the details of this have actually been published in journals and publications that are accessible to everyone. The main report by the NFER is in the middle, shown in the middle here, and this you can download from our UnLocke website or from the Education Endowment Foundation. We have 2 initial academic publications, one in the Journal of Cognitive Enhancement, which talks about the details of the pilot study, and then a more accessible version, which targets educational practitioners in the Journal of Emergent Science, which people can look up if they're interested in kind of reading about it a bit more. So next slide. So here's the kind of executive summary, overall summary of what happened in the intervention. So this is a typical results table from the Education Endowment Foundation. Here, what we're doing is really measuring the impact of the intervention on primary year 3 and year 5 children's performance on a standardized math and science test. And this is a typical table that you will find in the Education Endowment Foundation. Let me talk you through it. First of all, let's look at the column that says EAF security ratings. So it's got, they rate all of their interventions as on a 1 to 5 scale, actually a 0 to 5 scale, as to how reliable the findings are in terms of the implementation of the trial. And we have a very highly secure rating, which is 4 out of 5. 5 out of 5, I would say, is almost impossible to get, because I think pupil absence on the day of testing has to be less than, I'm trying to remember, less than 10%. And the national average for pupil absence on any day is 12%. So it's hard to see how many interventions could have more than 4 padlocks. But anyway, let's have a look at the result in terms of math and science performance. So the NFVR in their evaluation, what they did is they pooled the year 3 and year 5 data together because they weren't interested in any age particular differences. And if you take all the year 3 and year 5 children, which is about 2,700 children, what we find is that they have an improvement relative to the controls of approximately 1 month's additional progress, with an effect size of 0.09 for those that are interested. And this improvement is not quite statistically significant, so the kind of magic number is 0.05. The likelihood that this is not due by chance has to be less than 5%. So it wasn't quite significant for the math improvement. However, the science improvement, year 3 and 5 pooled together, was equivalent to 2 months additional progress in math and science on a sample of 2,735 children. And here it was statistically significant. The EAF also give a cost rating. This is a very, very low cost intervention. We'll give you a little more detail about that when we move to the next slide, Derek. Okay, so what we can say, as I said before, is that relative to the control groups, the children in the stop and think intervention benefited by 1 additional month progress in maths and 2 additional, although not quite statistically significant, 2 additional months progress in science, which was statistically significant. But if you think about that in terms of the investment, it really comes out to something like £5, less than £6 per pupil, and only 7.5 hours input. So, 1 or 2 months progress with 7.5 extra hours of input is really quite a good return. I should say this is not extra in terms of adding on to the curriculum, but rather it's embedded within the existing hours of practice and so forth. Derek, next slide, please. So in terms of the overall reports, because we had suggested it would work both in math and science, and the results in maths are not quite statistically significant, the evaluators were unable to conclude that the program worked overall. Okay, but they were happy to conclude that it definitely worked in maths, and that the effect sizes in, definitely worked in science, and the effect sizes in maths were of significant value. Looking more carefully at some of the analyses that are reported in the report, some of those other contrasts and comparisons we can make, what we do find as well is that the year 5 children did better in both maths and science when compared to the active controls only. So if we just take the year 5 and compare them to the group that's going to rule out placebo effects, they were better in maths and science. So it had an impact on both math and science performance in year 5. We found the biggest effect size, the biggest potential for effect in the year 3 math groups for children in free school meals, so low SES children. Now, it was not statistically significant. That's because we didn't have enough of these in our sample to draw reliable conclusions. The sample was not powered to draw reliable statistical conclusions on this. But this is a really promising finding that actually has kind of encouraged the EAF, the Education Endowment Foundation, to go on and trial this a second time on a larger scale, targeting low SES children in particular. And yeah, okay, and Derek, if we can move on to the next slide. And finally, in terms of inhibitory control training, we found in our own post-testing no evidence that the Stop and Think program had an impact on pupils' general inhibitory control as measured by pen and paper task. Now, remember that we weren't trying to train them to get better at inhibitory control. We were simply trying to teach them, to train them to use whatever level of inhibitory control they had within the context of math and science. Here, what we were doing is measuring outside math and science whether it had impacted on their inhibitory control, and it hadn't. But obviously, the improved performance suggested it had, the improved performance in math and science suggested it had worked within the context of math and science. So this is actually a finding that's fairly common in these kind of cognitive training things, that pupils, participants show improvements in the context in which they're experiencing the training, but it doesn't generalize, transfer to other domains. Derek, if you want to push the button, thank you. So what about, the qualitative analyses? What did the teachers think about it? And what did the pupils think about it? Well, one of the first conclusions that the NFVR had report on is that the majority of teachers thought that Stop and Think had a positive impact on math and science abilities in pupils. So this was definitely the case, or at least it wasn't statistically the case, but it was definitely the case in the low SES kids. Year 3 kids. Derek, next point. However, even though they kind of noticed this positive influence on their children's behavior, and then we measured that it worked in science, it did have an effect in science and maybe not in mathematics, or less so in mathematics, the teachers interviewed did not endorse the rollout of the program in its current form. And there were a number of reasons for this. Those included things like the difficulty of adding yet another new thing into their busy day, their curriculum. I think there's a slight misunderstanding there, because it wasn't meant to be an additional thing, but rather replacing 10 minutes for a few months, for 2 months. Some of the software we had was a bit glitchy. Children these days are used to very slick, high-profile computer games, and I'm afraid we were an academic research team, so our computer games were not as exciting as Minecraft. But that's something we've been working on in the second version. And issues of pupil engagement. Some of the year 5 teachers felt that the material was too simple for their kids. Now, remember, we weren't trying to teach them the curriculum material. We were trying to teach them to stop and think. But ironically, it's interesting that we found the strongest effects in year 5, right? So the teachers might have thought it was inappropriate, or the kids might have been complaining that it was too easy. But maybe that's when you need to stop and think. Maybe it's when you're really confident that, oh, this is so easy, I know the answer, that you make those kind of incorrect misconception errors. And then it's actually in the easy problems that you need to stop and think most. So next slide, please, Derek. So here's some statements from the teachers that kind of illustrated their kind of appreciation of it. So for example, one teacher said it allowed me to develop my understanding of how children in my class learn. So this is a kind of indirect benefit of using this, shedding light on the learning processes for the teachers. It gave me insight into how children's ideas can change. And then it showed concepts in a different way. It got children to think about their learning. So it has an indirect impact on teachers' reflection and practice, as well as on children's math and science performance. And Derek, next slide, please. Okay, that was it. So I think, Derek, I'm going to hand over to you. I thought we had a slide with some quotes from children, but some of the quotes reported in the NFR report really just mirror what the teachers were saying, that some of the children said, oh, it helped me stop and think, and then I used it in other classes and so forth. So there were some examples of children really transferring this to practice in other domains, not just math and science. Derek.
Brilliant. So now you've heard what we have to say about the project and what happened, is back to what do you think? Going back to the 2 questions, what might this mean in the classroom, and how can the research be better used to inform and influence practice? Some of the things that we're thinking about, and we'd like reactions to that. So it's over to you. I'll just stop sharing the screen. So if you want to put your videos on, you're welcome, and ask questions. And if there are any questions in chat, I don't know whether there are at the moment, but please indicate if you'd like to ask a question. Happy to take them live, as it were, by putting your hand up. Use the a raised hand sign. Whoops, what have I done now?
I guess I can, if nobody, I'm one of these people, I'd be a terrible counselor because I can't stand silence, right? I know that, you know, counseling techniques, you wait till someone else breaks down, but I'm going to break down before you. You know, please, and any input you have. I guess one of the questions I'm interested in is, I mentioned at the beginning that we developed this through a computer interface. We're thinking of having a non-computer thing. I mean, is it worthwhile, do you think, to try to develop a lower tech version of this, or is that going to make it less interesting? Just...
Can I, oh, sorry, there's someone else.
Maureen, do you want to go?
Hi. I teach a lot of students with ADHD, but I teach in the secondary setting, right. middle school setting. And you just talked about the paper-based kind of approach to this idea of just, for me, it's about drilling this idea of stop and think all the time into the kids. And I've got my own little paper version. It's a 3-step kind of trying to externalize executive function a little bit and get kids into the habit of just paying attention in class. And I mean, I wish you guys could just invent some sort of chip that we can shoot into their brains to make them actually pay attention.
I'm not sure we're allowed to do that. But...
I'm sure some of my parents would give you their consent. I don't really have a question. I wonder, yeah, I mean, it's great. I think it's really great research, and so, we need to use the technology to sort some of these really uninhibited kids out. Sorry, that's all.
Yeah, so I mean, just to follow up on what you were saying, I mean, you know, some kids find the computer aspect of it more engrossing, so engage with it more. We found in practice, in the real world, there's so many technology issues with, you know, some schools. This was primary. Also, the technology keeps evolving, right? So this stuff at the moment doesn't work on Chromebooks, and everyone's moved to Chromebooks, and then they're all going to move to tablets and then to phones. So it needs to, we have to be constantly, we need if this is going to be rolled out, then there needs to be some kind of actual commercial you know, technology company that wants to update things as well. The one thing I was going to say, Maureen, is that you have your paper version, and you know, these things, something called the pause moments has been around for ages, right? One of the key things we found is that embedding it within the particular domain is really important. So not just general wait and stop and think, but doing it in the context of the math or in the context of the science.
I
so
have versions for each subject.
Perfect, great. Because then it becomes a condition. They associate that with, oh, I'm doing maths, I have to stop and think. And it becomes this conditioned association rather than a kind of general training, which doesn't really associate with. But
the only way it really works is if the teachers are relentless, the parents are relentless at home, and the kid is on board with any of these things, I feel like.
Yeah. I mean, you know, certainly your group of kids are more challenged in this regard.
Zoe, you had your hand up.
I'll just find my unmute. Yes, thank you. It's a similar kind of question. I work for NASEN, National Association of Special Educational Needs, and I was wondering where, you know, one of the problems you pulled up about what do these blocks, what number do these blocks represent? I was wondering, similar to the lines of Maureen, the ADHD, pupils with ASC, what effect, is it a language barrier rather than a stop and think as well? I wonder what research you're going to look at moving forward with that, really.
So in terms, okay, so there's a whole bunch of questions in that. So I'm sure you know very well. So, you know, if you take a group like ADHD, there are multiple dimensions of difficulties, right? So, and it's hard, we shouldn't lump them all together and say they're all the same. So some might have language, some might have others, and so forth. I think the other thing is, I think you were focusing on the idea of misconceptions, that that we have this kind of deeply ingrained initial responses, like, you know, what do cows drink? Milk. Oops, that's wrong. And I personally am not continuing the research into misconceptions. Where I was more, I'm more, you know, I work more on kind of inhibitory control sorts of things and so forth. But I do have colleagues at the IOE Institute of Education who are looking at that. And one of our team members here, Emily Farron, who's now at University of Surrey, is actually doing some work on misconceptions. And I believe that as a function of, as a consequence of this evaluation, the Education Endowment Foundation are now in collaboration with NatSen, I think, are now developing a kind of tool, evaluation tool that, or instruments that would be standardized and would allow you to kind of evaluate what level of misconceptions in math or science individual children have. So teachers could use this. Because there's a lot of work on it, but it's kind of diffuse and spread out in lots of different articles. And so there's a much more interest in looking at where these misconceptions come from. And, you know, I suspect there will be, that one size won't fit all, right? There will be different strategies for different children in terms of helping them overcome those. Note that misconceptions is not just children, right? I mean, we as adults continue to have them all the time. The electric circuit issue problem that Derek showed at the beginning, even though we have done this presentation many times and talked about it many times, Derek and I and my colleagues still sometimes get it wrong when we explain it because the misconception is so strong.
Did I get it wrong today?
No, you didn't say, no, you didn't. But that was not an indirect comment. So, you know, adults have that as well, of course. Yeah.
Yeah, but I think the whole issue of misconceptions fascinates me because I was involved in the space project about 30 years ago. And part of it is about being able to help make things explicit for the children and to recognize that if you've got a wrong answer, actually that's natural because it's part of learning. And I would argue that very often we only learn when we get things wrong.
Yeah, I'm a big advocate. When I was teaching, that was my whole thing about getting things wrong is the route to getting things right. You know,
absolutely.
To overcome that, and pupils with additional needs tend to struggle with that a lot more than our pupils that are more neurotypical.
Yeah. And before I go, just give my regards to Adam next time you see him.
Okay, Derek, thank you. Yes, I'll pass on your regards.
Sally, did I see your hand up earlier? And I've got Kendra marked up as well.
It was kind of covered with what Maureen was talking about, so
okay. Kendra, you got your hand up?
Hi, yeah, thank you. That was so fascinating. Thank you very much. Along with Lisa, who's here as well today, we're involved in initial teacher education. And I think it helps us think differently about how we talk about conceptions and misconceptions with our trainee teachers, really. So we're kind of shifting away from this holistic conceptual change idea to this sort of parallel ideas, and you have to kind of move into the right domain for the right situation. And I just wanted to say that's really helpful in all sorts of ways, and links quite nicely with more social views of learning as well.
Yeah. I mean, I think it's, you know, there was a model at one point saying that you know, misconceptions or early concepts were replaced by later, more advanced, quote, more advanced concepts and so forth. But in fact, there's a lot of evidence suggesting that these things coexist. And part of the problem is selecting what is the right one for the right context. So, you know, the example I give all the time is about trying to teach, you know, year 1 kids, or even year 2, wow, that the earth is round, right? I mean, it certainly looks flat, and you get endless reinforcement that it's flat in throughout your life, and when you're playing football, it feels flat. Yet you have to learn that the earth is round. But that doesn't mean you should replace your flat earth concept with round. I mean, frankly, when they leave the classroom and go back out to play football, they better believe it's flat, right? Otherwise, it's all going to go horribly wrong. So you have to understand, you know, there's this kind of juggling of concepts, and what is the right concept? What is the right idea in a particular context? And I think that's something where executive functions or inhibitory control, managing knowledge, is actually something that we're realizing plays a much more important role than maybe you know, we thought previously. So I see Tony has.
Tony?
Yeah.
Yeah, I think you really do need, I mean, I'm a past it mathematician, but I think you really do need to think carefully about which misconceptions are sort of God-given and which are taught.
Okay.
Most misconceptions are taught. And it seems to me that the wording of your materials exacerbate this. I mean, what number is shown by the blocks? That doesn't have any meaning, but you're choosing to give it a meaning by counting the little squares. Which of these animals are fish?
Mm-hmm.
Well, that's a convention. You're referring to some inner workings that are not visible.
Right. Yeah.
So that's not really a misconception. That's simply a technical distinction. What worries me more is when you didn't have on show of -5 being smaller than -1.
Yeah.
Nobody in mathematics, I mean, teachers do use such language, but they shouldn't, because nobody really thinks -5 is smaller than -1. The expression is less than.
Yes.
Okay. And it's less than is different from smaller than. In fact, -100 is really quite large.
Yeah.
In some sense.
Yeah.
So one can create misconceptions where there aren't any, and hence miss the ones that are actually interesting.
Sure. So
that's my worry.
Yeah. No. I 100% agree with you. Back in the dark ages, I actually studied math and physics myself at university, so I completely understand what you're saying. A couple of things to say. First of all, we recognize that the wording and some of the problems you set were not perfect, and that's one of the things that we've been kind of working on with feedback from teachers and so forth in the second version. The second thing is, I agree with the conventional issue, and even with regards to counting things. I mean, the kind of rods and sticks are conventional materials that the children in year 3 and 5 will be familiar with. So partly we're kind of addressing or using some of the knowledge as well. I completely agree that the distinction between whether it's a mammal or a fish is based on internal function, and they have to have some kind of theory of understanding. But again, we're teaching them conventional information. The other thing to keep in mind is that here, the curriculum items we're targeting year 3. So we're talking about, I'm trying to remember here, year 3, 7 and 8, and year 5 children, which is 9 and 10 children as well. So they don't do negative numbers. So that's not one that we could put on and so forth. So we have to kind of adapt. You know, it's very important that this inhibitory stuff is within the context of what they will be reasoning about. So we should really adapt it for the curriculum level. We did a little bit of work on this with secondary school pupils, not a full intervention, but a study which was looking at years 7, 8, 9. And so we were able to kind of explore slightly more complex concepts and misconceptions. Again, we took the misconceptions out of textbooks about it. And I 100% agree with you that some of those are taught and whatnot. I think, well, my final point on this is one of the kind of contradictory misconceptions that is perhaps God-given, as you say, that we address, are the ones where you have perceptual evidence which contradicts or appears to contradict a more analytical approach. So a classic example of this is one that we've used with the secondary school pupils is, I don't know if you can see my fingers. Oops, I can't do this. I'm terrible. I'm terrible. All right, let's imagine you have an angle. My fingers are aligned, right? And you draw 2 arcs. One is really close to where they cross and one is far away, okay? So far away, you've got a bigger angle, sorry, a bigger arc, but the angle is always the same. And you can show kids, you know, 2 versions of the angle with the arc close by or far away, and you say, are they the same? Or is one bigger? And they'll almost always go, well, the one with the bigger arc is bigger. In fact, that's wrong, but it just looks bigger perceptually. And so you can have these conflicts like the the one that Derek showed at the beginning with the circles and an environment, which is giving you a kind of context which changes it. So that is one form of conflict, a kind of perceptual regularities versus analytic regularities. The perceptual stuff just jumps out at you. And you have to overcome that. So the stop and think would help with that as well. So those are just my thoughts on your response.
Zoe?
Would that not be, sorry, going back to the language as well, because the misuse of the word, as Tony's just said, less, fewer, smaller, bigger, larger, rather than it being a stop and think, an inhibitory response. It's more to do with a language. I understand why you've gone back to look at it, because I'm fascinated with that use of English to teach maths with, as being an inhibitory factor for maths, to be quite honest.
Yeah, no, I agree. I mean, it is fascinating, and having the right wording is essential. And that's possibly about teacher training more. But you know, one of my great examples. So I do some work in some actual hands-on work with primary school kids, you know, in the classroom. And I remember a lesson where this was year 2 kids, and they were trying to teach them about money. So, and you know, some of them have got it, others just haven't got it. And they had different coins, some pound coins, and I don't know, 2 pound coins and a 5-pence piece. And then the other ones had, so that's 3 coins in total. And the other ones had, I don't know, 5 coins, right? 2 20s, a 5, and a 1p. Is that right? No, I need another one. That's two 1p's. And the question was, you know, which one has more, right? And of course, the question is alluding to the value, but it's obvious that there are more coins than the other one. And that's partly, you know, the choice of language, of how do you express it to the kids. Because I remember this one particular child that I was working with and trying, he just wasn't going in. And eventually he kind of circled the right one. And I could see, as I went on to someone else, I could see he was watching me. And when he thought I wasn't looking, he rubbed that out and circled the one he thought was right, you know, which is of course wrong. So they really didn't go in, right? He really was committed to his perceptual understanding of it. So yes, use of language is absolutely critical as well.
Sally, do you want to explain your comment about STEM sentences?
Yeah, it's just that, I mean, obviously that ambiguity of language, you know, the more we try and get pupils to discuss the maths that they're doing, the bigger that issue of ambiguity becomes. And that's where, you know, the recommendation, you know, in the DFE guidance, for example, there are those kind of the language, the recommended language, those structures that all children can use to describe what's going on accurately, you know, with careful selection of, you know, whether I'm using fewer than or greater, you know, less, smaller. And I think, you know, the more that we can be doing that with children, the greater, you know, the lesser the likelihood that they are going to get those misconceptions.
Yeah. I think it's one of those situations where the more that we become aware of some of these issues, the more we can do about it. And it isn't a single factor. It's actually quite subtle, some of the changes and the impact that we need to think about. But if we're not aware of it in the first place, then we're not getting anywhere. And we're actually making it worse. And I think that is the problem, coming back to Tony's point. Quite a lot of misconceptions are taught in a way that because the teacher hasn't thought about how it might be interpreted by the child when you actually use that particular context or that language or whatever. And I think that's what keeps coming back on all of this. And I think going back to the whole misconception stuff, there are piles and piles of articles on misconceptions, but some of them were very, very simplistic. And you could almost translate them as being, what funny ideas can we find out from the kids today?
Yeah.
And actually, it's so much more subtle and deep than that we need to bear in mind.
Yeah.
Any more questions? Or are you all content that it was worthwhile coming tonight?
Good.
Yeah. In that case, I'll just go back and share my screen just to finish off.
Can I just make one point, Derek, beforehand? Before you
Yeah.
go, just one final thing is just to say to everyone that there's more information about this on our webpage, www.unlock.org. And as I mentioned, the education. Oh, sorry, Derek, you're about to say it. I'll leave you to keep going.
There was another slide. Yeah. No, carry on what you were saying, then we'll just finish it off.
I was going to say exactly what's written here. So I was going to say that the, yeah, go on, Derek, you say it.
No, obviously we've been doing dissemination events and we're getting the publications together, but we don't have any specifically planned, but obviously we're happy to contribute if anybody would like us to. Before the pandemics and lockdowns and all of that, we're actually trying to address the question of how do you get projects and interventions like this that have shown some promise into classrooms. And we had started some work with Kent where teachers were looking at the various interventions, and 2 or 3 schools asked if we would present UnLocke to them so they could try and use it in their schools. So that might or might not be resurrected. We've been revising the software, as Denis said. We've got this effectiveness trial coming up, which is being done completely independently from us. It's not going to have the research assistants supporting the schools. So it's to find out whether this activity could work in the wild, as it were. And the plan is to have something like 175 schools and nearly 9,000 children. But that's been delayed for about 12 months. So we're expecting that in 2022 coming up. And if you need details, then it's on the EF website.
Yeah.
And that's where it is. Which reminds me to say that the slides of this presentation will be on the website, on the Learnus website. And I should have said beforehand that it has been recorded. So if you do want to listen to the presentation again, it will be on the Learnus website. And if you don't want your pieces that you said on that, we'll have to chop them off. So please let us know. So I think that was it. Have I missed anything, Denis?
No, I was just going to say that the recruitment for the effectiveness trial has started, even though the trial is paused. If you're interested, or your school is, or you're in a network of schools who might be interested, if you just go to the Education Endowment Foundation website, you can just click, add a name and email, and it'll just be an expression of interest, and they'll contact you with more details of that. We can't do research unless there are people who volunteer to take part of the research. So it's hugely important that if you or anyone you know would be interested in seeing this. I mean, the fact that we already have effectiveness results that are positive should hopefully encourage people to take part.
And it's just for years 3 and 5.
At the moment, it's just for years 3 and 5. So, if they find results, meaningful results, significant results in this trial, then I think what happens is it gets kicked up to yet another level where they will put more resources into it in terms of developing better IT, I guess, but also, it needs to be, the problems, the issue, the content needs to be developed for each curriculum. Just one final comment is we did have someone, it unfortunately never got off the ground, but we were going to try it in year 7 pupils with, who arrive at school with a lot of kind of holes in their knowledge or difficulties in math, particularly. That's something that if there was a school that was interested, we'd be keen to try it as well, but that would be very experimental. And see whether it works with the same content in slightly older children. But, oh, well, there we are. Maureen, perfect. If you're interested in trying it with them, we can have a chat about that.
Brilliant. So with that, I'll just say that on the 18th of May, I think it is, we have another Learners webinar, which is Resilience and Wellbeing in a Pandemic. And details of that will be going out fairly soon. But if you are interested, it's there. So I hope, well, from your comments, obviously you've enjoyed it and found it of use. And thank you for coming. And if there is anything, do get in touch and we will do what we can to help. And so with that, enjoy the rest of the evening.
Thank you very much.